see guys I haven't seen for years.
Right.
We're all getting older.
Yep.
You know, and as I got older, I find I dislike driving great distances for a short meeting. If I'm going to drive someplace, I'm going to drive and spend the night or something like that if it's more than 3 hours. So it really.
Yeah, I put my Zoom bridge out there for clubs in the San Joaquin Valley section. A couple of them took me up on it for a meeting, and then somebody went out and got their own. But it's nice, right? It's nice as a section manager to just plug into somebody's meeting and not drive to Bakersfield or Fresno or Lodi.
or Lone Pine.
Yeah.
You know, your Lone Pine's in your district, John, and that's
I know.
that's a good 14-hour, 15-hour drive. You got to drive down to Mojave and then 2 hours back up on the hit 395.
That's a 2-day trip someday.
Yeah.
Dean, I'm trying to decide if that's your picture or if your video is stuck.
Be in here.
Yeah, you could do that.
Oh, there you go. Your video was stuck.
To go to.
Okay, here.
Come on, you could come join me.
Not
I can make you get it. There you go. You disappeared. You're too far back.
There's trick photography. Go here.
Okay, well, the clock just flipped over. So I think we should start.
No.
Can you do it?
Got 50 so far. I'm sure there'll be some stragglers coming in. So just to introduce myself, I'm David, WD6T, and this is the Northern California Contest Club meeting. Now I'm going to share my screen, and hopefully you'll see some slides if I do this right. You see the slide? You may have to find the video that has it. Yes, no, maybe?
No, Dave.
You're not seeing it. Okay, now why is that?
Not yet.
Select it. Okay, sorry. Wrong. Okay, there we go. See that?
Yes.
Okay.
Got it.
Great.
Yeah, that'd be great. Yeah, thanks.
Okay, so oops, not that one. So let's see, how do I get to the next slide? That's interesting. Oops, it skipped several. Okay. So this meeting is the Northern California Contest Club, but we also opened it up to other clubs. And so first, a little bit about who we are. We're a large contest club in Northern California. The URL is NCCC.cc, so NCCC.cc. So it's one of the best URLs out there. .cc is Cocos Keeling Island, which a lot of us know from DXing. But apparently I guess they made some money by selling domains. So a lot of people use .cc's and works great with our name. So if anybody who's not a member, I invite you to go to the website and check it out and learn more about us, and maybe think about joining if you like contesting, love contesting, don't know what contesting is, or any of the above. We could always use more contesters, and it's a great sub hobby and really a lot of fun. Now, in particular, every let's see, July, for the last couple of years, we've had a joint meeting with the Motherlode DX and Contest Club. And we couldn't do it this year for obvious reasons. They had a meeting scheduled today. And so we decided that, or they decided to forego their meeting, put Case 6 SRZ on hold until the next meeting. He was the presenter, and invite everybody to this meeting because we have a special guest. So I just wanted to, is W1RH on or?
Yeah, I'm here. I'm dialed in, not on my usual computer, so probably some feedback. And I'm on the phone, so you can make me shut up, but I'm here. Thanks.
Okay, good to hear you. You got a little bit of echo, but did you want to say anything?
Okay, I turned down. I think the echo's gone now. No, I don't have anything to say. This is going to be a great meeting, and I'm glad we got so many in attendance. And carry on. Glad to be here.
Okay, thanks. Well, welcome to everybody. And also, I reached out to some other clubs. Redexa, another big contest club in the northern part of the Bay Area. West Valley Amateur Radio Association down on the peninsula, the Stanford Amateur Radio Club, the Palo Alto Amateur Radio Association, and FARS. I'm not sure if the latter two got the message, but I sent them a message, so maybe some people got it. So here's we always like to list some upcoming contests. You can always go to contesting.com and see the contests for the week or contests for the whole year. But here's some that are coming up. The IOTA contest is today. It lasts until 5 a.m. in the morning. And there's some good DX on, hopefully. Then next weekend is the North American QSO Party CW contest. That's a 10 or 12 hour contest, domestic mostly, but lots of fun, multipliers per band. We really like it. After that is the Workdoll Europe DX sideband contest. Another DX contest, probably a bit challenging unless you have big antennas, but interesting one. Then the sideband version of the NAQP, of the North American QSO Party. Then the Hawaii QSO Party, which usually amounts to a handful of people who get on a lot of bands, and you can use assistance, and they get posted to the DX spots, DX clusters, and you can go find them and work all Hawaii. And then WW Digi is a contest that was started by W0YK and others, and it's just started last year. It's all FT8 and FT4, or I guess you could use any digital mode, but it effectively is all those modes, and great for small stations and people interested in those modes. And it'll be interesting to see how many people get on this year with the shelter at home. And in general, there's been a lot of increased contest activity because of the shelter at home, although decreased de-expedition activity. Okay, then the North American Sprint, CW Sprint on the 13th of September, and finally the first really big contest of the year, the CQ Worldwide RIDI contest on September 26th. Okay, now I wanted to just take a moment and remember two people that we lost very unfortunately in the last week or so. First one, N6GD, Greg. He was the secretary of the NCCC. He was very active in West Valley Amateur Radio Association. He was an RF engineer, really nice guy that many of us knew. Well, he operated an N6RO as well. This is a picture of him at Field Day at West Valley. The other one is W5FU Grady. He's a giant in contesting, a good friend of W7RN, and built several stations with W7RN, including the Comstock Memorial Station. So let's just pause a minute and remember them. And okay, moving forward here, some good news on the contesting front. I guess it's not a secret anymore that that NCCC won the WPX radio teletype contest. It was a major effort on our part, a focused contest, and it was great that we won it. Other noteworthy achievements in the ARL DX contest. 8 Papa 5 Alpha came in first as single operator high power with 6.7 million points. And in the highly contested single transmitter high power, that's multi-single, ZF1A, which included our W9KKN and also some guy named N6ML and N6WIN and K6AM. Came in with number 1 at 5.9 megapoints, and right behind them, P40L with W6LD, W0YK, AE6Y, and K2LE, many of whom are members, maybe all. I'm not sure about K2LE. But anyway, great effort, great achievement, and congratulations. And there's I sent an email to the reflector, to the NCCC reflector, with some of the other nice achievements of NCCC members in recent contests, including these two. And going on, where I didn't want to take too much time here because really want to hear from our speaker. So let me tell you a little bit about her. So our speaker is actually, before I go on, I just want to see, is there any questions, and especially from the non-members about NCCC?
Pardon?
Okay, I guess not. And I'd like to ask you that once the presentation starts, to mute your audio, because it'll make it easier for everybody else to hear. So, okay, so Sandra Faber, whoops, I've got the bio here. She's a university professor emerita at UC Santa Cruz, where my daughter is, by the way, and a staff member of the UCO Lick Observatory. She's an observational astronomer with research interests in cosmology and galaxy formation. Some of her major discoveries include the first structural scaling law for galaxies, which is named after her, the Faber-Jackson law. Large-scale flow perturbations in the expansion of the universe caused by superclusters of galaxies, and supermassive black holes at the center of galaxies. In 1984, she and 3 colleagues presented the first detailed treatment of galaxy formation based on cold, dark matter, which became the standard paradigm for galaxy and cluster formation in the universe. She was one of 3 astronomers who diagnosed the optical flaw in the Hubble Space Telescope and played a major role in its repair. She established the scientific case for the twin Keck 10 meters telescopes, which inspired a subsequent wave of giant optical telescopes around the world. From 1994 to 2005, Faber was the principal investigator of the DEIMOS spectrograph, which is a large optical multi-object spectrograph for the Keck 2 telescope, and it's the most powerful instrument of its kind in the world. She and her colleagues used it to conduct the DEEP redshift survey of the distant universe, which collected spectra of 50,000 distant galaxies and exploited the immense power of Keck to see and study galaxy formation 10 billion years back in time. She later co-led a project called CANDLES, the largest project in the history of the Hubble Space Telescope, which extended our view of galaxy formation back nearly to the Big Bang. She received her BA from in physics from Swarthmore and her PhD in astronomy from Harvard. She's a member of numerous organizations, including the U.S. National Academy of Sciences and the American Academy of Arts and Sciences, the American Philosophical Society, and she's a fellow of the Royal Astronomical Society. Recent awards include the Bauer Award and Prize for Achievement in Science from the Franklin Institute in Philadelphia. In 2002, she received the Bruce Medal of the Astronomical Society of the Pacific and the Russell Prize of the American Astronomical Society for Lifetime Achievement. And other recent prizes include the Gruber Cosmology Prize from the Gruber Foundation and the Magellanic Premium from the American Philosophical Society. And somewhere in there, I'm missing something, but oh yeah, there it is. She received the National Medal of Science from President Obama in February 2013. And in July 2020, she received, or I think she just received or will receive, but the gold medal of the Royal Astronomical Society. So now I'm going to stop sharing my screen and hopefully Sandy's ready to go. Let me find my screen sharing.
Okay, so I want to share my screen. Here we go. How are we doing? People can see?
Yeah.
Yes.
Great.
All set.
Ma'am.
Are you going to be playing any audio?
Unfortunately, yes, but I'd actually like to get rid of it. I couldn't figure out how to mute a video and be heard on a Zoom at the same time. So if you have a way of killing my audio, that would be, except for me, that would be good.
If you didn't share it, when you share your screen, it asks you if you want to share your video, your audio. And if you didn't check that box, it should be okay. And then you can just mute it locally.
Let me check that since this is important. I guess I'll stop share and start over.
You sound just fine, Sandy.
Well, the problem is when I play this video, I want to speak over it. I don't want to. It's not asking me about sharing my audio. So let's just proceed. And we'll see what happens. Okay. So glad to be with you all. And in this new age of the pandemic, I find that I'm speaking to audiences that are larger than ever before. I was giving a talk sponsored by a university in Santiago, Chile a few weeks ago. And at one point I had 2,000 people listening to me. So courtesy of their hard work in advertising and putting it all together. So it's a really wonderful experience, and I hope to share some ideas with you. So let me just give you a little background. First of all, here's my title, Cosmology, Meaning, and Human Destiny. So from that title, you will infer that this is not quite the average cosmology talk. The first part of it is, but the last part of the talk is much more philosophical because more recently, after retiring, I've had time to think about the significance of cosmology, my work in it, but the larger field. And I'm convinced it's pretty important and it should be better known to people on Earth. And if it were, it would have larger implications. But I don't think these thoughts are generally agreed to by everyone on the planet by any means. So I'm going to throw out some ideas at the end of the talk, and maybe if there's time, we can have a discussion of that. But let's start at the beginning in a more traditional way. For the first part, I'm just going to tell you the cosmic story of the beginning of the universe and how galaxies formed and how our sun and solar system formed within our galaxy. So it's like reading our own personal cosmic roots, but astronomers provide you with the first several chapters. This is our joint human cosmology, our cosmic myth. Okay, so now I need to advance my slide. There we go. I find it useful to start this talk with a video that kind of sets the stage. It was made by a friend of mine, Brent Tully, at the Institute of Astronomy at the University of Hawaii. And it's a fly through the galaxy and then out into intergalactic space. It kind of sets the scene. So we start this video by flying towards Orion. And as you can see, Orion tends to disappear because it's not a real thing. It's just a lineup of stars along the line of sight. And it has two glowing gas clouds in it, the Orion Nebula, which we're about ready to fly through, and then the Horsehead Nebula behind. And these are regions where extra gas happens to have accumulated inside our galaxy. And there's enough self-gravity there to bring it together, making a new generation of stars. The light of the stars is very, young stars is very intense, ultraviolet ionizing radiation, lights up these gas clouds and causes them to glow. So they're signposts of new stars forming in galaxies. And now we're flying past another ionized region, which is completely different. This is the Crab Nebula. It's an expanding gas cloud from a supernova about 1,000 years ago, and you can see a little pulsar flashing there in the middle. That's the dead star. And now this is the part of the video that I really like the best. I think it's a quite realistic rendition of what it would look like if we could fly out of our own galaxy and see it from afar. And the people who made the video, Brent, chose a nearby spiral, 5383 from the Southern Hemisphere, that is thought to look like our own. Now, these other little blobs are appearing are the Magellanic Clouds and other satellites of our galaxy. And now the view is going to pan around to the other big members of the local group. This is a smallish spiral called the Triangulum Nebula, M33. We're going to fly through its big H2 region. And then off there in the upper left of the screen is the Andromeda Galaxy with its small elliptical companions. And now the view pans out into intergalactic space. We're going to fly through past some very familiar galaxy images for those of you who have amateur telescopes. And this distribution of galaxies is really based on Brent Tully's own work. He has mapped the local supercluster. And of course, not every distance is perfectly known, but you get the general idea that the galaxies are not uniformly distributed in space. They tend to be distributed in filaments. We're flying down one filament now, and the filaments intersect in giant clusters, and we're about ready to reach the center of the Virgo cluster, which has about 1,000 galaxies in it. And right at the center lurks this giant elliptical galaxy, M87, which has one of the biggest known black holes in its core, weighing almost 9 billion solar masses at the very middle. So this was a quite realistic rendition. The pictures of the galaxies are as they actually look. Only one thing has been done to make it more watchable, and that is the sizes of the galaxies have all been multiplied by a factor of 10 so that you can see them. And if they were realistic size, then they would be barely visible. And that gives you a better feeling for how empty intergalactic space actually is. Okay, well, so much for this beautiful film, setting the stage. Where did this all come from? Where did these galaxies come from? Where do their shapes come from, their sizes, and their distribution? Because galaxies are the building blocks of the universe. Without them, the universe would be structureless, a boring, empty, uniform soup. So what does it take to form these fascinating objects? So let's go back to the very beginning, 14 billion years ago, and think about the early universe. It was almost smooth in density, but there were density fluctuations there at about a part in 100,000. And the time when our physics begins is 10 to the minus 35 seconds after the Big Bang itself, when the temperature was 10 to the 27 degrees Kelvin. Okay, stupendous numbers. And so at that time, the universe was expanding faster than the speed of light. I'm going to come back to this topic. And when universes do that, they actually generate fluctuations from a quantum process. And those little fluctuations are small, apart in 100,000, and they have peaks and valleys. And every one of those peaks in the subsequent evolution serves as a little bit of extra gravity that draws in matter around it. And by the same token, a valley lacks that attractive power, and so it loses energy. And you can see that this is an instability. It runs away. A peak grows and valleys get deeper and deeper. And the net result is that the matter falling on these original little quantum peaks, each one of those made a piece of a galaxy. So now we can simulate these things in the computer. And this movie was made by my colleagues at Santa Cruz several years ago. It was really a forefront of visualization at the time. There's a theory for these peaks. And so you can make a model in a computer, you can put them in the right place. And this hunk of space here was constructed by them to be the early Milky Way. So this is a picture of how the dark matter in the universe clustered to make our own galaxy. Let me start this up. There we go. Okay, so the universe is expanding, but the peaks are growing. And one of the ways they grow is by absorbing other peaks. So small peaks fall into bigger ones and so on. And that process is called hierarchical clustering. So what we see forming here, we're focused on the very center of what's going to be our Milky Way. And it's a very busy place. All of these little sub-peaks are drifting around in the larger potential of the Milky Way and orbiting it. And there are some other subsidiary peaks, like for example, that one coming across the bottom of the screen might belong to the Large Magellanic Cloud and so on. All right, now you're probably wondering at this point, a galaxy doesn't actually look like that. We don't see galaxies with all of these satellites in them. So what's going on? And the answer is that what we just saw was a picture of the so-called dark matter, which dominates matter in the universe about 5/6 of the total. But dark matter is just that, it is dark. It only interacts with itself and with other matter via gravity. And so you can't see it. It doesn't make stars, it doesn't shine, it doesn't respond to the electromagnetic force, it doesn't emit photons, etc. What does do that is the normal matter of the periodic table, which is about 1/6 of all matter. So you can think of galaxies as as entities in which the dark matter sets the tone, and then what you actually see is a frosting of fireworks, star formation, and light emitted by the ordinary matter. So my next video, this is the objectionable one that might have sound, is a picture of the same sort of thing, a rendition of the Milky Way, but now what you're seeing is the gas, it's blue. The gas falls together and makes stars, which are pinpoints of light in this. And again, it starts out with small blobs, which then merge to become bigger blobs. But you will see that the physics is radically different, and that is because ordinary matter can collide, the gas clouds collide, whereas in dark matter particles, they're free to go past one another. So let's look at this. If there's no sound, I'll talk, but otherwise I'll be quiet until the end. I got to start it here. There we go.
From the beginning of space and time, gravity has shaped the fate of matter. There are two types of matter: ordinary matter, like gas, dust, and stars, and dark matter, which dominates the universe. Yet dark matter is only known to us through its gravitational pull on ordinary matter. Here, clouds of gas are blue and stars are yellow. The dark matter is unseen, but its gravity helps the gas to clump together and form a galaxy. The first stars form where the gas is densest. As more gas falls into a galaxy, it creates a rotating disk. Stars begin to form there too, and eventually, a disk galaxy is born. This galaxy is growing by cannibalizing other galaxies that formed first. As mingling collections of stars pass by each other, their gravitational interactions stir up a spiral pattern. Maybe all spiral galaxies form this way. The first galaxies formed this way, early in the history of the universe. Our Milky Way galaxy, with its spiral arms of gas and dust, and hundreds of billions of stars, began this way. In less than 2 minutes, we've witnessed an evolutionary journey of 4 billion years.
Okay, so let's cut it off there. Did you hear the sound for that?
We heard it, but it was a little hard to hear what she was saying.
I see, okay. So if I can just summarize the gist is the gas falls in at the beginning, it begins to make stars. The hunks, the proto-galaxies collide. When they collide, the stars are thrown into halos that create sort of spheroidal components. An additional disk falls in and reforms a rotating disk galaxy. So we expect from this kind of logic that galaxies are going to be components of spheroidal stellar objects through which are threaded gaseous disks with more stars in them. And whether you're mostly spheroid depends on when your last major merger occurred. If it was recent, then your disk was destroyed and you're all spheroid. If you're pure disk, that might happen because you've been isolated for a long time and have not suffered any major mergers that disturb your disk. So that's the basic idea. And now, how do we know that this picture is right? There are many reasons, but I'm just going to mention 3 here, 3 tests. The first test is the properties of galaxies as we see them today. The second is something called the cosmic microwave background radiation. And finally, the third is we can actually look at galaxy formation back in time by using big telescopes like Hubble, which enable us to look back into the past. So let's consider these, the properties of galaxies today. Major point, galaxies do exhibit both disks and spheroids, just like the models predict. So here are 3 galaxies that are mostly disk galaxies. And here are 3 galaxies that are mostly spheroidal. And as I say, we pretty much understand this change in morphology. And if I can draw your attention to the edge-on disk in the lower left, look at its dust lane there. It, along with the disk of stars, it's got gas and dust grains in it. I'm going to come back to those dust grains in a little while because they're very important. But that offers us an opportunity to compare to the morphology of our own galaxy. This is a wide-angle picture of the galaxy taken in Chile. And you can see the presence of a central spheroid there and a flattened dust layer that's in the disk of the galaxy. So this is how we know we're a flattened spiral. Okay, the second point is the fact that the cosmic microwave background from the Big Bang has the right pattern on the sky, as predicted by this theory of quantum fluctuations, because those density fluctuations started out very small, but then began to grow. And when we look back in time to when the cosmic microwave background radiation was last emitted, which happened when the universe was about 1,000 times smaller than it is today, those fluctuations were still small. They had not grown very much. And it's quite easy to predict their spectral pattern, their spatial distribution pattern on the sky. And in one of the great triumphs of theoretical cosmology, here's the observed spectrum. What we're looking at here is the strength of the dot pattern, the measle pattern, as a function of the size of the measles. And there's a characteristic size here that's about 1 degree in size, that's about twice as big as the full moon, where we predict a strong peak in the pattern, and indeed that's what we see. And in fact, we can predict the whole pattern all the way from much larger to much, much smaller than that on the sky. So this tells us that there were early fluctuations, and moreover, we know how to compute them. And then finally, there's proof number 3, and that is actually looking back in time to see whether our theories of evolution fit distant galaxies. And a prime tool for doing that is the Hubble ultra deep imaging. Here's the size of the field on the superimposed on the full moon, so you get a sense of how big the field actually is. It's not very large, just a few arc minutes across. Here is the picture that was taken. Absolutely gorgeous picture. There are about 10,000 galaxies in this image, and it's thought to be absolutely typical. If you aimed in different regions of the sky, of course, you would see different galaxies, but the kinds of galaxies and the number of galaxies, their brightness properties and so on, in this picture are predicted to be representative. So the wonderful astronomers at Space Telescope Science Institute have made this more vivid for us by making a video, which we're now going to look at, which actually flies us down out in space and down the arrow of time in a portion of this field. Here it is. So now let's look at the video that they've made from this. The point is that we now have methods which allow us to estimate the distance of every one of these galaxies. And the makers of this video have placed them in space along the line of sight and then had the camera fly through them. So what we're doing is we're looking at galaxy evolution backwards in time. And all the big galaxies, we passed them, and everything now is very small and very blue because it's full of young stars. And this one is red because it's so far away that it's very redshifted. Okay? So this confirms our suspicion that galaxies started out small and then merged to become larger. And we now have hydrodynamic models that are computing this whole process in the computer, and you can make very detailed comparisons with the pictures of galaxies that Hubble has taken. Okay, so there are about 100 billion galaxies on the celestial sphere. And there are about 100 billion stars in our galaxy. So that's a lot of stuff altogether. And some people look at this and they feel really sort of insignificant. So I thought I would sound that theme by making an astronomy despair poster. I don't know if you guys are familiar with the despair posters. I think they're hilarious. They're little pictures that are often cute and captivating, but then underneath there's a completely deflating caption, which is discouraging, demoralizing, and demotivating. So here's my astronomy despair poster. Cosmology, finding out you really just don't matter. And you know, that is a message that some people internalize from all of this vastness. But as it will turn out by the end of my talk, this is exactly the opposite of the message that I want you to take away. So I'm sort of setting up a straw man here. I'm going to come back to this point in a minute. But first I want to finish our own cosmic origin story. And we've made the galaxy now, and now we have to make stars. So as I noted, stars form from dense clouds of gas, places where the density is big enough that the self-gravity of the cloud causes it to collapse. And here is this galaxy we flew through in the Brent video, Messer M33, and that's the H2 region that Hubble has taken such a beautiful picture of. And it's a very typical H2 region, and you can see all the new young stars there at the center. And Hubble, some of the most beautiful pictures taken with Hubble have been regions like this in our own and other galaxies. Here's a region called the jewel box. It's making a star cluster. When those young, bright stars form, their ultraviolet radiation ionize and excite the surrounding birth clouds. This, I think, is my single most favorite Hubble picture. I just love it. The new stars are up there at the top, and they are sending out a photon rain in all directions, and the photon pressure, radiation pressure, is sculpting pillars in the cloud, kind of like the rain sculpts pillars in Bryce Canyon. And as it happens, there's a star forming deeper in the cloud, and it's excavating its own cave. So it's a little star cave in there. Okay, so by great good luck, there's a very active star forming region not far away. We flew through it. It's the Orion Nebula. And Hubble has taken a mosaic of the whole region, and the frames have been put together, and Hubble's fabulous resolution allows us to enlarge, enlarge, enlarge. And finally, we get to a point where we can see stuff that is silhouetted in front of the glowing gas clouds. So this frame here shows us two such objects, a big glowing object and a smaller, elongated, roundish, dark object with a red point in the middle. And it turns out that there are around 50 of these things altogether in Orion of the two types, and around half of them are the large extended kind, and the other half are the small, dark silhouetted kind. And we interpret these as solar systems and stars in various stages of formation. So early on, the cloud that a solar system would form from would be still large and fluffy. We might see embedded within it a nascent protosolar nebula. Here's another one here. And often these clouds here are getting blown away by the neighboring big stars whose photon rain is very powerful, photon wind. And in fact, maybe some stars are completely disrupted that way by their bigger brothers. But if you're lucky and manage to survive, then all your material condenses to make something that looks like this. This is the young star, and it's surrounded by a disk of dust and gas. And the dust itself consists of these little dust rains, each one about the size of cigarette smoke. But when you put a lot of that dust together, it actually becomes opaque. And we know that those are rotating disks because, very fortunately, we can see one that is edge on. Here's the star. Its light is sort of peeping over the top and the bottom. And this is a rotating disk and 17 times larger than Pluto's orbit. This is about the size of the sphere of comets around the solar system. So our solar system probably looked like this. The inner part made planets and the outer part made comets. So this gives rise to a picture of a rotating protosolar nebula that is in which the dust grains are very important and they're very sticky. They stick together. Gravity at some later stage tends to bring them together. And what they're doing is they're actually making rocks. And they're going to make rocky planets like Earth, but it's also thought now that big planets, gaseous planets like Jupiter, their cores are all rocky too. So these dust grains are the trigger, the force for the formation of planets regardless of size. That's what the current theory says. Okay, so here's our rotating protosolar nebula, and we can see within it, we can see various objects here of different size, all the way from tiny grains to asteroids, and asteroids that will collide to make rocky planets. So I especially like this next picture, which I think sort of sums up our situation so beautifully in the galaxy. Out the mouth of the cave here, what one can see is the center of our galaxy. That's the center of the spheroid, which is very bright, and this is the disk. And you can see silhouetted all of those dust grains. And in the foreground, you see the rocks, which are the result of the dust grains coagulating together and collecting in the formation of our own planet. And so right here, you can see us as we are today and where the material for the Earth came from. It came from those dust grains, which I should say are manufactured in the envelopes of stars. Stars are making heavy elements, and those heavy elements now can coagulate to make these little dust grains. So we're all stardust, including the rocks of the planet. Okay, so now we've made Earth, let's consider Earth in context. But before we do that, I have a little chapter here on the fate, the large-scale cosmology of the universe and how it expands. So we need to begin this chapter with a review of what is in the universe, what comprises it today. There are two kinds of matter. I've been talking about them in my talk. The so-called dark matter, which is the non-interacting but very prevalent matter that creates the scaffolding for galaxies. And then the normal so-called baryonic matter, which is the matter of my kitchen here as I sit here, the matter of the periodic table that makes stars and planets. Okay, that's the matter. And over here is something called dark energy, which I have not talked about so far because it's only recently, rather recently discovered. And I want to, in the next couple of sentences, compare and contrast dark matter with dark energy. So dark matter is matter. It generates an attractive gravity, and this causes the universe to decelerate, just the same way that a rock thrown up from the Earth slows down because the Earth attracts it. In contrast, dark energy is completely different. It generates a kind of repulsive gravity, which causes the universe to accelerate, actually to beyond the speed of light. And this is a phenomenon that we call inflation. So why are there these two different things with such different consequences? It's very simple. Regular matter becomes more dilute as space expands. The number density of particles goes down. And that, when you put that into Einstein's equations for the expansion of the universe, causes a decelerating universe. Dark energy is weird. Its energy density stays constant as the universe expands. And when you put a material like that into Einstein's equations, it generates repulsive gravity. And this effect, an expanding space, together with a constant energy density, you can see we're not obeying any more conservation of energy. We're creating both new space and matter energy at the same time. So this is one of the total paradoxes of the universe as we know it. This process has been called by Alan Guth the ultimate free lunch. Okay, so here is a summary of this. This is a rather nice graphic. Time is running horizontally here, and the Big Bang is right there where my cursor is. I hope you can see it. So time is going this way. And at each little bit of time, a circle is plotted, which indicates in a relative way the size of the universe at that time, or let's say a size of the visible universe that we can see. So the key point that I want to talk about right now is this early part, come back cursor, where this is so steep. Okay. This is normal expansion out here, and this is the microwave background when the universe was 1,000 times smaller than now. But before that, you can see that the expansion was much more rapid, much more precipitous, and that's the inflation era that I've been talking about. And when did it actually occur? It occurred, it began around 10 to the minus 35 seconds after the nominal Big Bang itself. And it only lasted from, in the classic theory, from 10 to the minus 35 to 10 to the minus 32. So it was practically nothing. And yet the universe is thought to have expanded by at least 100 orders of magnitude in that brief period of time. Okay, so here's to get us oriented, this is the afterglow of that pattern here, seen here in the picture of the microwave background. So as I've said, the microwave background is full of fluctuations, and the fluctuations, that's the same fluctuations that made galaxies. So we need to talk more about these fluctuations, which I think are probably the most remarkable part of the whole story. Let's imagine I have a little energy density measuring meter, and I'm flying through the early universe right after inflation ended. And I'm measuring these density fluctuations. There are thousands of a percent, which is about a part in 100,000. So let's enlarge a small part of this pattern. We see that there is a peak there. Now, why is there a peak there? That's because of a combination of two things. First of all, quantum fluctuations in the energy of the background. So there's something called the Heisenberg uncertainty principle, which says that any system you want to consider, its energy is not a fixed number, but is actually varying all the time. So let's zoom in on a small little portion of this space that is expanding during inflation and consider the energy density in that little space. It's going to be fluctuating. This is going on right now. It's going on right now in my kitchen and your kitchen. The difference is that space is not expanding today, and so these fluctuations can find each other and go away. But imagine that a fluctuation appears and space is expanding extremely rapidly, then pieces of the fluctuation get torn apart, and the little quantum fluctuation is now macroscopic. It can't find itself anymore to die away. It's frozen in. And actually, those of you who have thought a little bit about black holes and Hawking radiation that's emitted from the horizon of a black hole, this is really, the expanding universe in inflation is really a black hole that's expanding outwards rather than collapsing inwards. So what I'm talking about here is the fluctuations that correspond to the Hawking radiation of an inflating universe. How big are those little things? Well, they are about a billionth as large in physical size as the size of the smallest elementary particles that we have today. So when I say they're quantum fluctuations, they really are extremely small. And yet that peak, which is so small there, at 10 to the minus 32 seconds at the end of inflation, the now regular ensuing expansion of the universe is going to make it expand to the size of the Milky Way. And it's going to wind up being 100,000 light years across, and it will have dragged in much of the matter around it. So here in this picture, we're looking at the seeds of the density fluctuations that made galaxies. Okay, so let's review some of the consequences of this first inflationary period. First of all, whenever we have an inflating universe, we are creating matter energy. We have this energy density, space gets larger, and we have a larger volume of that same energy density. We now have more space with the same density of dark energy. We've gotten something for free here. We've seen that it creates these density fluctuations, which lead to galaxy formation via standard gravity. And so, to summarize, This period of inflation, together with quantum noise, are the creative duo of our universe. This is why we have space that's big in the first place and why we have structure within that space that made our galaxies and therefore us. Okay, so if you were paying attention, you heard me talk about first inflation. And that's because there's evidently now a second inflation. So if you look very carefully at this diagram, you see sort of regular normal expansion for a while, but now the expansion seems to be accelerating rather recently, but things are sort of curving upward there. And that is due to the fact that we've discovered dark energy in our universe today. There was a separate dark energy that caused inflation right after the Big Bang. We actually understand that dark energy. It's called the scalar field of the grand unified theory. And it has all the properties that we need in order to have it create inflation then at that early time and high temperature. But we did not anticipate the fact that there seems to be another kind of dark energy coming in late in the universe. This is, as I say, a recent discovery. So let's review the consequences of this second inflation, which we are now entering the era of. It's rather recent. The universe has only had time to approximately double under the influence of this new dark energy. But the consequences are profound. Let me show that to you by having you consider a galaxy now, when the age of the universe is 14 billion years, just about. Consider a galaxy that is 10,000 kilometers a second away from us today. What will it do in the future? Well, the size of the universe is doubling every 11 billion years, and it turns out that that means that the velocity of this galaxy will also double in that period of time. That's what I mean by the acceleration. Galaxies are not just going away from us, they're going to go away faster. And so in 25 billion years, 11 billion years from now, that galaxy will be going 20,000 kilometers a second away. So follow this logic down through the table, and by the time we get to 69 billion years, the age of the universe, that speed of the galaxy will be 320,000 kilometers a second. And of course, you'll remember that the speed of light is 300,000 kilometers a second. So now this galaxy has accelerated to go faster than the speed of light. That's one of the things that can happen in a universe. It can't happen in a laboratory, but it can happen when gravity acts, or negative gravity acts over large scales. Things can actually move faster than light. And this is not weird, because we all know that if we have a black hole and drop something into it, then it reaches the speed of light as it goes through the event horizon around the black hole. And remember, I said that an accelerating universe is really a black hole inside out. And so all of these particles around us are accelerating away, and there's a sphere, another sphere, event horizon around us, where all of these objects are going to reach the speed of light. What happens to an object as it reaches the speed of light? We don't actually ever see it do that. It becomes redshifted and dimmed before that. So what's going to happen as this galaxy approaches this critical speed is it's going to get dim and it's going to disappear, and it has a finite photon emission rate, so there will be a second at which point the last visible photon from that galaxy reaches us. It keeps moving, but we can't see that anymore. And so effectively it's redshifted out of sight. It's no longer part of our visible universe. And we believe, unless something happens to this dark energy term in the meantime, that that's what's going to happen to all the galaxies that we see, except for the ones that have already fallen in and collapsed and made the local group. The local group is bound by its own attractive galaxy, gravity, but everything else around is free to be accelerated and will disappear. And so if we were cosmologists, something like 60, 55 billion years from now, if intelligent cosmologists are still around, they will have no universe to see and study. And unless this information that we are getting now, when we can see the universe, is archived and preserved, it will all be lost. And I would wager there will be no way that they could observe anything that would tell them where they came from. All the evidence for that will be gone. Okay. Differences between the second and the first inflation. Let's summarize that. The second inflation is occurring now when the energy density in the universe is much lower, and that means that the energy density of the dark energy field that's driving second inflation is much lower. Second inflation started only recently, one doubling so far. First inflation was temporary, and that is because it was created and driven by the scalar field of grand unified theory. We have some general ideas about how that field evolves as a function of time, and it's generally predicted that it will decay away, and that's why inflation stopped. And we pretty much understand that. At least we have the gist. By contrast, the future of second inflation is unknown because, one thing, it's very recent. We haven't had it for very long. And the problem is we don't know if it's going to be constant or whether this field too will decay away. We just don't understand that. If it were constant, then we could call it the cosmological constant, lambda, which is a famous term in Einstein's equations. Einstein actually put in a term like this with repulsive gravity. And the problem is that we have no known explanation for the magnitude of this dark energy today. This lambda term, if indeed it is a constant, is very, very small. And you can make sort of natural units by combining physical constants. And when we do that, we get an energy density called the Planck density. But this field is 10 to the 120 times smaller than Planck density, and there's no theory for it. So it's a great mystery. So the fact that we seem to have a dark energy which doesn't have any natural explanation, a number that's sort of plucked out of nowhere, is an example of something called the fine-tuning problem. And I want to spend some time talking about that. Fine-tuning is a situation in which there's a physical constant in our universe that seems to be picked or designed or specified exactly so as to make the universe that we see. So one of the major philosophical questions in cosmology today is, where did these basic numbers come from? Lambda is one of them. The mass of quarks is another. The size of big G, the gravitational constant. All of these physical constants that we're so familiar with, why do they have the values that they do? Okay, so now there was a big flash there. And the reason was I wanted to introduce logic, which many philosophers of science and also of religion have invoked. Aha, my gosh, this is an amazing constellation of numbers. There are about 100 of them altogether. And you can do thought experiments. You can change these numbers, and you don't change them very much. Some of them are very sensitive. You change them by 20%, and say chemistry as we know it completely changes. This is the best evidence, cosmic evidence for a God that made our universe exactly this way so that we could be in it. Now, I'm not a religious person, but I am a cosmologist. So how do I answer this question? I answer it in a completely different way. And the way I approach it is something called anthropic reasoning. And I invoke as my alternative to God something that many cosmologists are now, this is becoming a respectable idea, something called the multiverse. So I ask you to consider a situation in which there's a machine out there that is churning out universes in huge numbers. And the key point is that they're all different. Our universe is the way it is because it's one of the few whose parameters are in the range in order to support our kind of life. So let me give you a familiar example. Let's imagine we went back to Greece and we're Greek cosmologists talking to ourselves, and we're asking ourselves, why is the radius of the Earth approximately 4,000 miles? That, to a Greek, would look like a constant of the universe. The Earth was at the center of the universe. This special object has a radius of 4,000 miles. Why? Well, we know the answer today. The answer is because our human species is adapted to life on a rocky planet of roughly that size. We can't live on a gas giant. We could not live on a planet 100 miles in diameter. It wouldn't have no atmosphere. We could not live on a planet that's 20,000 miles in diameter. The gravity would be so strong that our bones would collapse. So you and I and all the other life that we see here is adapted to this number, 4,000 miles. And we know, we can now explain this because there's an ensemble of, a very large ensemble of planets out there, and they have all different masses and radii and so on. And our planet is picked out of that ensemble because we are on it. So this logic, which people despised for many years because it seems like sort of backward reasoning, is now becoming more and more respected, and it's called anthropic reason. And similar reasoning explains why the sun is the way it is. We're not around an OB star because it would have too much ultraviolet radiation, why the solar system is the way it is, why the planets are spaced the way they are. Not all solar systems are like us. And why our galaxy is like the way it is. Not all galaxies are like the Milky Way. So it seems perfectly reasonable to see if we can explain the universe this way. And this is my preferred explanation, that there is a gigantic number of universes out there, all different. And we can't see them, but they really exist. And ours is one member of that ensemble with its properties because we're in it. Now, it would be nice if we had some theory to make that ensemble of universes. And one of the great developments of my time as a cosmologist has been supersymmetric string theory, which is a theory for the structure of elementary particles, in which particles are vibrating high dimensional strings, and their vibration properties, each string vibrates differently, makes electrons here, makes gluons there, and so on. It turns out that supersymmetric string theory is a multi-dimensional theory with 11 dimensions. And it says that our universe was created out of an original 11-dimensional entity in which little pieces, our piece, 4 dimensions expanded to make our space and time, and all the other dimensions remain rolled up and make the particles in our universe. So the magic of supersymmetric string theory is that you can get many different versions of it from the same basic parent theory. And each one of those versions could make a universe with different physical laws. So let me summarize this. This theory solves several key problems in cosmology. For one thing, there is a new particle that is predicted by supersymmetry that's a candidate to be the dark matter. Has not been discovered yet, but nevertheless, it's still a very attractive candidate. This theory can produce, once in a while, a small cosmological constant or value of dark energy, although that would be very rare. It has a quasi-infinitude of possible solutions, each one of which would be a universe with different physical laws. And it can generate these universes in an endless stream by a process called eternal inflation, in which this substrate, this 11-dimensional substrate that I was mentioning, is itself inflating. And in the process of inflating creates, these inflating bubbles create different universes. They're all separate from one another. As far as we know, they can't communicate with one another. There's no way of actually seeing that they're there with a real experiment. Although people are working on ways to do that. Okay, so I've said some pretty outrageous things. I thought it would be fun to summarize ridiculous notions in one slide. It is ridiculous that we can actually talk meaningfully about processes at 10 to the minus 35 seconds and a temperature of 10 to the 27th degrees Kelvin. That's ridiculous. It's ridiculous that a vacuum, which is technically empty, it has no particles in it, can actually have an intense energy density that can affect the motions of particles embedded in it. That a universe can expand faster than light and matter energy spontaneously appears when this happens. That a quantum fluctuation smaller than the smallest elementary particle can grow to become a galaxy 100,000 light years across. And as a result of this quantum issue, the Milky Way is really like Schrödinger's cat. Schrödinger's cat is this famous example in which the cat, a macroscopic being, is hooked up to a quantum system, the radioactive decaying atom. And when the quantum event, the decay occurs, it affects the cat. Before that, is the cat alive or dead? The cat is killed when the atom decays. And you know, there have been decades and decades of speculation about what this really means about reality. My point here is actually the galaxy and all galaxies that we see are examples of Schrödinger's cat. So there's really no way that we can just sweep all of this stuff under the rug and say, well, that's a quantum problem. It has nothing to do with us. Far from it. No, this is how we were created. Okay, for anthropic reasoning to make sense, we have to assume that this multiverse really exists even though we've not seen it. And a question is this kind of reasoning scientific? And I've made the point, yes, it is. It's actually been the most creative form of reasoning in cosmology thus far. And so here's a thought summary that we can discuss after I've finished speaking. Inflation is a generic process and is responsible for both the multiverse and everything in our universe. It is the creator of everything that we see. It's why we exist. It's the closest thing that physics has to God. So I leave you to contemplate that, and perhaps we'll have some discussion. Okay, I want to turn now very quickly to Earth and planets in our galaxy. Here's a summary of planets that we've seen. We now have candidates for 4,000 of them. And the question, I think, the important philosophical question for us is Earth rare? So there's something called the habitable zone around stars. That's where water on the surface of a planet can be liquid. And there are probably many Earth mass planets in habitable zones. But not all planets in a habitable zone are in fact habitable. And we have two of them in our solar system. Venus at the inner edge and Mars at the outer edge are technically in the habitable zone, and yet we know that things happened to them, they went bad. And this causes us to think that there are many more features of Earth that are essential for life, not just being in the habitable zone. And I've listed them here, I won't go through them. Maybe most surprising of all that you haven't thought of is the existence of the fact that we have a super big moon around the Earth. That turns out to be important for Earth dynamics. Now, it's okay for Earth to be very rare if the planetary ensemble that it's drawn from is large enough. And that question is addressed in this wonderful book, The Rare Earth, Why Life is Uncommon in the Universe. This is kind of a contrast to the Drake equation, which you probably heard of, which predicts that there are a lot of Earths in the galaxy. By contrast, these authors have tried to find all of these various factors, and as a result, there are more terms in their equation than the Drake equation. The number of suitable stars, N star, is around 100 billion. There are 10 terms in this equation, each one of which is no bigger than 10%. And when you put those terms together with n star, you get 1. Now, I'm not saying by any means that we know the answer to this, and we don't. This is why we need to find extrasolar planets and characterize them. But if you want my opinion, Im-ho, Earth as it is precisely as we know it is extremely rare. That's my predilection. And it informs a lot of my thinking. I'll come back to that in a minute. So, okay, we've got Earth. What are we going to do with it? And to think about that, we need to think about Earth's cosmic future. So what are the cosmic threats to intelligent life on Earth? There could be a nearby supernova whose radiation would sterilize the planet. The sun is slowly aging and warming up. Asteroids can hit us. Our dynamo may fail because the center of the galaxy, of the planet freezes, it's cooling, and we'll no longer have a magnetic field, which protects us from solar radiation, ice ages, and so on. There's a long list, but it turns out that actually the most surprising and hardest to predict is volcanoes. And they have produced the largest extinctions in history. And there's even a theory, you know, that at one point our species was down to 1,000 individuals, and all the rest of us were killed by a volcano. And this was around 75,000 years ago, so this theory goes. So there's very little we can do about volcanoes in the future. Aside from that, there's a high probability from all these other features and factors that we have at least a few 100 million good years to play with on our Earth. We're extremely fortunate. This is a beautiful planet and a beautiful solar system that's very reliable. So now I'm transiting to the philosophical conclusions of my talk. What are the lessons that we should take away from cosmology that I've just reviewed? Well, first of all, lesson number 1, we got here according to the laws of physics, and we are subject to those laws and must live within them. There were no miracles in our past, and there will be none in the future. We have to live with the physics we got. And then lesson number 2 is that Earth is likely livable for at least 100 million years and maybe longer. And so we have been given the precious gift of cosmic time. Are we going to use that well, or are we going to squander it? This is the challenge of today. And what's really interesting is that we are the first generations of human beings to have this broad understanding of cosmic history, to know what could be ahead of us and what we could exploit, what wonderful things we could do with 100 million years. Nobody has really thought in those terms before, no previous generation. But the great irony is, of course, is that we are the first generation of human beings to have the power to erase that future, at least for us, not the planet, but its livability for our species. And these two things obviously go together. The very technology that we have developed in order to do all the science that I've told you about is the same technology that could prove to be our undoing. So I think that thinking about 100 million years completely changes our concept of sustainability. So we know that economies like to grow at 3.5% per year. That's considered to be kind of normal economic growth. So supposing that goes on for 100 million years, what happens? It's actually hard to do this on an HP calculator. They really can't quite handle the numbers that are needed. Okay, but that's the result. 10 with 1,500,000 zeros after it, a big number. So what is the point? The point is that sustainable growth on cosmic time means no growth. And in addition to that, it means no net increase in resource use and waste reduction to levels that can be completely naturally recycled. Over cosmic time, the slightest imbalance, either in pollution or resource consumption, will grow and become and escalate out of sight. So if we're contemplating living on our planet over cosmic time, we have to be in perfect balance with that planet. And we really haven't come to grips with what that actually means. So, you know, when Al Gore was running for president, he had just made this movie about conservation and sustainability called An Inconvenient Truth. And so there was this cartoon that his movie is over here, An Inconvenient Truth. Nobody wanted to come to grips with that, so they would prefer to go to the movie called A Reassuring Lie, which is telling everybody that the current system is just fine and there's no problem ahead. I actually think that the real truth is closer to this. People are going now, gradually coming to grips with the inconvenient truth, but cosmic reality is much, much harsher than any idea that anybody has floated so far for sustainable growth. When I hear the word sustainable growth, I really want to, well, I won't use the word. All right, so all of this to me brings new moral issues to the fore. What are our obligations to future human generations? Do we have a custodial responsibility for Earth if Earth is common, if Earth is rare? Especially if it's rare, you see, because we already feel custodial responsibilities for special portions of our own planet, like national parks, Yosemite, and so on. We protect those. Should we be thinking in terms of galactic planetary parks for planets of special beauty with special properties, and should Earth be one? So I'm appealing to our nascent custodial responsibility sense that we already have for pieces of our own planet. Should we begin to apply it to the planet as a whole and treat the planet differently? But really, what we're getting at here is whether there's an intrinsic value to the future avenues of humanity. Does humanity have a destiny? Does it have a goal of any kind? And this is a way of discussing the future that no one is discussing. Nobody is talking about a question. Well, supposing we polluted the planet and higher intelligent life disappeared from our planet. What would be lost to the universe? We really need to have a discussion of values. And the minute you talk about values, the issue of a moral code comes up. Do we have a moral code for the future? I think we do not. I think we have evolved to this point without needing to think about the far future. All we need to think about is tomorrow and how we will eat, and maybe 30 years from now, and how our progeny will survive. But nobody in our past has had to think about 100 million years. So we don't have those muscles because they've never been needed. This brings up the question of where moral codes come from. I think they're evolutionary based. I said genetics based here. Some people, many people, think that they're religiously based and come from God. Will either sets of moral codes be able to adjust to this new reality? That's the big challenge. So I'd just like to tell you briefly about the Earth Futures Institute at UC Santa Cruz, the only institute of its kind. And why is it unique? First of all, it has this focus on cosmic time, which, as you can see, changes the nature of a discussion of sustainability. And it raises the question of the ethics of the future. Why do we want to do these things, and what will be lost if we don't do them? And as far as I can tell, no one around the planet is really raising this very deep issue. So let me conclude with some pictures, because I think pictures are a good way to tell stories. This is an unusual picture of Saturn taken from the Cassini mission, which flew around to the back of Saturn and looked back towards the sun. It's a truly amazing picture. It's not doctored in any way. That's what Saturn looks like from the far side. Now we all see that it's a picture of Saturn, but it's actually a picture of something else. So if you look really close there, you can see some dots in the picture. And one of those dots is special. That's Earth, as seen from Saturn. That's Carl Sagan's pale blue dot. And by gosh, even in our own solar system, from the planet Saturn, golly, do we ever look rather insignificant. This is the makings of another despair poster. Cosmology, finding out you really just don't matter. But if you've been listening to my talk, you can see actually that my thrust is quite different, that actually I believe that Earth is rare, and at the very least, we have enormous cosmic possibilities given to us by the gift of cosmic time. And so with that in mind, I would like to put forward a different kind of cosmology poster, cosmology inspiring us to save the Earth for future generations. So I've thrown out a lot of kind of half-baked crazy ideas, and I'm really interested in whether or not you folks resonate with these moral issues that I put forward. Do you think they're important, and how should humanity address them? Because frankly, I think we only have less than a few decades to worry about these things and do something constructive. So I'll stop there and open it up for questions. Thanks.
Those people are muted, but I'm sure they're all clapping. That was amazing. Well, I'll start off here, but I can't quite answer the question you just said, but I have just a couple of questions about what you talked about. One question is, so why does the anthropic principle require the multiverse? Can it just be that things just are the way they are because that's the way they had to be for us to be here to ask how they are, but doesn't require other additional universes where they're different?
I think if you get rid of the multiverse, all you've done is you've dragged in God. Okay, because we have one example and you're back facing the question, why is that one example the way it is?
Okay.
So that's something important about the anthropic principle, which I think is not sufficiently emphasized. The unseen ensemble is an inevitable consequence. And if you reject that, you reject the argument.
I see.
Stop your screen share.
Oh yeah. Why don't you stop your? Yeah, there you go. One other question is when you talk about the size of the universe, this is always something that's hard to get your head around. So let's say at the very beginning, the universe is very small. So what does that mean? That means that if you're in that universe and you can somehow move around, no matter where you go, you stay in that universe.
Yes.
So it's not in other words, if you're envisioning a clump of stuff with darkness outside of it, that's the wrong picture.
That's not good,
right.
Except insofar as this substrate of the 11-dimensional parent stuff is, you would be embedded in that.
Oh, I see. So if you can zoom out to 11 dimensions, then you might be able to see your
Exactly. That's right.
Well, let's open up to other people's comments.
I have a question. This is Andy in the other room here. If machines are going to be taking over, and I saw a prediction of somebody that by 2045, artificial intelligence could well surpass human intelligence. And of course, lots of thinkers think it will way surpass human intelligence. Is there any way to get machines to worry about these problems?
Yeah.
I certainly think we could get machines to worry about practical problems. For example, one of the things I think we desperately need, and if you know any folks with some extra spare funding out there who could fund our institute, this would be a proposal for that. I think we need rough estimates for what the carrying capacity of the planet is, and that's going to be a gigantic machine calculation. That is to say, can the planet survive with 7 billion people on it for 1 million years, or is it more like 50,000 people? And I think we need at least rough calculations to figure that out. I don't think that's really what you meant, though. I think perhaps you were asking whether machines could come to grips with moral questions. And I question that for a whole variety of reasons. I think our personal moral machinery comes from emotions. And I'm not sure that I know that logic can be programmed into computers. I'm not sure that emotional logic will ever be programmable into computers. So that's a limitation that I see. What do you think?
Well, my concern is that the machines will decide it isn't important. And these questions that are important to you and perhaps the other 7 or 8 billion of us are not important to the machines once they get sufficient numbers of them to satisfy whatever their existential criteria are, which I think will be difficult for us to control.
How do you pose importance for a machine? Let's say that a machine needs to know that something's important. How do you tell it that, or how does it figure it out that that thing is important?
Well, that's a question that science fiction writers have written about, getting back to Asimov's laws of robotics and things like that. And the question is going to be, in part, whether we can instill whatever we want, whatever we think machines should think about into machines, and prevent them from changing it to something that they think they should think about, which might be quite different, that we have no control over. And that's, of course, the kind of one of these issues about how we're going to survive if the machines decide that we're sort of inconvenient and don't want to share their resources with us.
You know what? Isn't this already happening like mad, though? My favorite example is computer-generated trading, which has all of these unforeseen consequences in it. And those machines are doing things that human brains cannot do. So in some sense, they're more intelligent than we are. They're certainly better at that job than we are. And people put software in them, which contains implicit in that is goals, weights of importance and so on, optimizing factors. And it's a complicated real life situation. And so what happens is different from what the programmers envisioned. I think this can happen all the time, but I don't see it as something that's really evil or insidious the way it's often portrayed when people talk about smart machines.
Okay, well, we can continue this discussion over the dinner table. We've got to let other people ask questions.
I have a question with regard to saving our planet, which I personally feel is extremely rare and such a gift. A lot of people talk about passing a tipping point in which any difference can be made. With your background, do you think that we have a tipping point? Have we gotten past it? Or if not, how long do we have before we sit here and argue so much and do nothing that we've already doomed our planet?
I think it would be wise to figure out what we meant by a tipping point. Tipping point for what? Tipping point for us? Tipping point for 7 billion people? Tipping point that would prevent even a few 100,000 people living on Earth? Let me give you an example. Some people say that as the climate warms, there is a tipping point which corresponds to ocean circulation. And there'll be something like a switch and the Gulf Stream will go in a different direction and the climate of Europe will be radically different. That would be extremely serious, that's for sure. But I don't think it rises to the level of a tipping point for the whole planet. Now, an example of a tipping point is Venus, which ran away with the greenhouse effect. But I think it's generally agreed that we're very far from that kind of tipping point. So first of all, A, I'm not an expert here. B, I don't think we really have models that are that reliable. And C, the general question of tipping point needs better definition. So I sort of haven't answered your question, for which I apologize.
No, but you've given me hope.
Okay. Okay. Well, I really want to ask you the question. Supposing 1,000 years from now, most higher life has disappeared from the planet. Is that good or bad? And why did you answer the question the way you did? Oh, and by the way, suppressed assumption. It disappeared because of actions taken by our generation and the next few generations that led to that. Is that, yeah. What's lost? And the crucial question is why? Will God be mad? That's one reason you could give. That's, I think, a perfectly good reason. Do you feel an obligation to future generations the way you feel an obligation to the current one? And if so, why do you? I'll stop there.
Well, good or bad to whom's perspective, the planet or the people?
Oh, well, that's part of the question.
Yeah.
I would say to the universe. I think we should fly at the very highest level.
I think people have a conscious or the ability to think and use and have a moral compass, at least that I recognize. I mean, animals might have the same thing too, but I don't know that for sure. And I think it would be a loss if we lost that life form that has the ability to think through problems at the level that we think. I know there are some animals like crows and things that can do that, but I like to think, and maybe it's just ego, that we have the ability to think on a much higher moral sort of giving level. We don't always show it.
Yeah, I mean, if you buy into the egalitarian or utopian vision of, say, Star Trek, the universe needs humanity, or something along that lines. But I suppose that does sound a little arrogant, doesn't it?
Well, I think there's a suppressed assumption there. Needs it to do what? And what is worse if humanity doesn't do that thing, and why?
Yeah.
But aren't we just wired to perpetuate ourselves anyway? Aren't we just stuck with who we are? The wiring that we've come up with is to perpetuate our own existence through ourselves and future generations. Do we have a way of thinking differently? I believe our thinking should be compatible and consistent with the way we're designed to function as an existing unit of whatever we are, human beings, so that we don't really have a choice. We have to perpetuate our own existence, and we have to do that in the best way we know how, and therefore it's immoral of us not to make decisions for our future and our future generations' ability to make use of the 100 million years.
Gosh, I like so much what you said there. It kind of reflects my own predilections and preconceptions. I think that our moral compass, such as it is evolutionary, and is the moral compass that a species have if they're a social animal and is constantly confronted. Each individual is confronted with what to do to ensure their own survivability and welfare versus recognizing that they depend on also the welfare of the group. It's the better angels of our nature. The devil is us, and the angel on the other shoulder is everybody else. And we constantly have to balance those things. My problem is, I think we're good at balancing them when the time frame isn't too long, but I don't know that we have any point of view even on how to balance those things. What's the transactional nature between this generation and far distant generations? That's what's troubling me.
Well, this is Andy, A6Y again. I have a thought, because I think the time scale you picked is very interesting, in that we know that the Earth will be destroyed by the sun in what, 4 billion years or some large number of years. It's hard to think in those terms.
Actually, yeah.
Yeah, on the other hand, we also know that human beings roughly 10,000 years ago were about the same as us, or fairly similar. We certainly know that going back to the Egyptians. 5,000 years ago. So it would seem reasonable that we have an obligation to try to preserve things at least on that time scale. We know human beings 1,000 years ago were very similar to us, for example, and we can read what they wrote, and we can for even 2,000 years ago. So it seems to me that I can import an obligation on that time scale. If you get much beyond that, though, it's very hard to say that we're preserving something for people like us, and that even our species will be adapting. And it kind of goes back to what I was saying about artificial intelligence in a way. And it may be that, you know, if you were asked the question 1,000,000 years from now, that's very hard to grab your mind around, that we will be humans 1,000,000 years from now, and that we now should have some obligation to those future things, which may be human.
But if we are evolutionary, isn't it all on the same continuum? So we're all part of the same continuum going forward, and therefore we do have an obligation to whoever our ancestors might be, and hence you can make no moral distinction at any point along the timeline because it's just a continuum. So you know, I think that it's thanks to Dr. Faber and people like her that maybe we're starting to think that way. And as we grow evolutionarily, we start thinking of those concepts in those terms as opposed to the way we have in the past. I'm sure our prehistoric ancestors didn't have too much time to think about anything but keeping away from the saber-toothed tiger or whatever.
I have a comment to that. So I love what you just said. Actually, what everybody's saying, including what Andy said. 1,000,000 years is interesting because there are some people who say that genetically a single species doesn't last longer than 1,000,000 years. I know you will think immediately of crocodiles. Haven't they been around here for 150 million years? And maybe they're an exception, but for higher primates and so on, it's sort of thought that 1,000,000 years, even if we didn't do any genetic engineering, we would wind up being different entities. That doesn't even fold in the fact that we are now probably entering what is, to my mind, the most dangerous thing of all. To heck with the environment. I think the real important thing that's the big danger is genetic engineering. And we're going to start to tinker with our genome, and we're going to want to fix cystic fibrosis, but we don't really know where the genes of the moral compass are. We don't know where the genes of the intellect are. They're diffuse, they're spread all over the place. And the minute we start engineering, we might have very unforeseen consequences. But on the other hand, maybe we could actually engineer a being with a new moral compass. Maybe over a long period of time, we're not a prisoner of our genetic endowment there. And finally, I sort of since we might be nearing the end of this discussion, let me just plant in your brain an even higher, more abstract thought, that what's really of value is this planet, which is so good at creating new things. And what would be lost to the universe isn't a species, ours, is not necessarily an intelligent species, us or our descendants, but the process, this cradle of creativity, rarity, complexity, always doing new things. And to shut that down, that to me, I'll just share with you my basic thought, that would be the most important loss.
I have one comment. You keep talking about humanity and not society. We're at a changing point for society at this stage. We are just, 1,000 years, 2,000 years removed in some places from hunter-gatherers, and we're still doing hunting, gathering, but it's called economy, where the greed rules. I want more. There's not enough for a lot of people, and a lot of people have got, I'm satisfied with a smaller house. I don't need the big mansion. I don't need a new car every year. But it seems to be the driving force of this new generation to get a new car every year. They've got to have the biggest house on the block. in as society, we have to change. If we can get society to change where, just like what Bill Gates says, we don't need to have families with 20 children, most of them dying, in order to get 2 or 3 that survive for the next generation that provides for mom and dad. So we need to look at the resources as a society and stop trying to gather in a greedy fashion, trying to provide for everybody, when as a society there's enough to go around. We just have to be satisfied, and that's the moral compass. It's not an individual moral compass. Society has to change that moral compass, and I'm off my soapbox.
No.
Maybe you would react favorably to the thought that we need a new religion.
Yes.
Oh, yeah. Yeah.
Sandy, I'd like to go back to your comment about volcanoes and volcanoes. It seems to me that we're dealing with, that we have in our hands something of almost volcanic power that we're taking massive risk with, which is the risk of accidental or deliberate widespread nuclear war.
Yeah.
And I wonder if you would comment about that and the existence of nuclear weapons from a cosmological point of view.
Yeah, I know it's a concern, but I have a colleague at Santa Cruz who is really studying very deeply technological developments, and he is worried much more about other things. So he's very worried about small weapons that are the size of insects and can fly around and land on you.
Right.
And
they're worrying too in terms of individual lethality. But I'm talking about sort of Earth scale modifications of the environment.
It's true that you would only kill one person at a time, but consider the effect on society that bringing down 2 skyscrapers in New York City had.
But you wouldn't kill the Earth.
Okay, I see.
To your point, you wouldn't kill
I understand your point now.
Okay.
What do I think? I don't think I have any thoughts that are particularly profound compared to any other thoughts on this topic. It's dangerous, and we're definitely playing with fire. There are people, the only number I've heard is people who are actually trying to compute the risk per year. It's said to be 1% per year. So
Right.
if that's true, then you can't go on much longer than 1 or 2 centuries. I don't know if that's a correct number or not. So I don't have much to contribute there.
Okay, thanks. And thanks for your talk this afternoon.
May I ask a couple of scientific questions?
Sure.
Sandy, this is Jeffrey Paulin. I'm just 2 very simple questions. I think, did I hear you correctly to say that in the universe there may be as much as 6 times as many elements as we currently have in our periodic table?
No, if I said that, I gave the wrong impression. No, if you just took a reasonably representative chunk of the universe and did a census of the matter, you would find that 5/6 of the mass would be dark, which might be 1 or 2 different species of matter, might be more than 1. And then 1/6 would be the good old elements that we know. So I wasn't inventing new elements for the periodic table.
Ah, okay. Thank you.
Yeah.
Somebody mentioned something in the chat window, and it's something that I've thought about when we talk about kind of, when you talk about our longevity here and how much time we have to act on some of these things. But if you look at just the sheer explosion of the population of this species on this earth, I mean, we're adding more brain power, more compute power, but we're also tapping, the resources of the planet itself. I think when you talk about feeding a formula into an HPC computer that would compute how much time we have to steward the macro universe from here, I think you would probably find that the computer would have an issue, would find that we're kind of perhaps out of balance right now on this planet.
Absolutely.
and that you know, that one of the things that would enter into the discussion is how the Earth creates and maintains that balance. When you talk about catastrophic, you know, for anything from self-destruction through, you know, use of the atom to whatever the Earth has for us to kind of try and manage that. And it seems like right now, if you were to run the numbers, it seems like a lot of the stuff that we're doing is being much like Andy said, is to kind of propagate our own species, right? And to make ourselves better and to help, you know, propagate the planet, you know, with us. But I have a feeling that, and I don't know what your thoughts on this are, but that would have to factor in, I would think, to your thoughts about how we would steward the universe and how much time we have to do that, and how out of balance we are right now.
Oh, well, I think we're like, with absolutely no reason to say this, I think we're out of balance by a factor of 100 in terms of the number of people that are sustainable. But I think that's one of the great questions that needs to be answered. This needs to be modeled. What are the limiting factors that set the long-term population? And obviously part of it, here's a moral question or a values question, is it's probably, you would find that you could have more people if they lived in a very much simpler, reduced lifestyle as opposed to a very lavish lifestyle. And so that's part of planning the future. Would you prefer to have fewer people living in tents? More people living in tents, or fewer people living a middle-class lifestyle? I think that has drastic implications for how many people can survive here over the long term. But you were talking about how we are driven to propagate, and that's true of most animals. This is part of the reproduction process. And many species have become so successful that they have led to their own doom. This is more the theme in especially the animal kingdom than the exception. So what we're talking about here today is really an extraordinary tweak or twist to normal genetic evolution. It would really be a radical, different restructuring of a species and what it does.
It seems to me that one of the challenges is that people have a really hard time thinking of the group as it grows. So they don't have too hard of a time thinking about their immediate family and the welfare of their immediate family, and not just thinking about themselves. And then you can expand that out to their neighborhood and then the city, and you know. But the further out you go, the more challenging it is for people to value that.
Right. But let me, when I'm looking for encouragement, I can think of some pretty profound examples in which our species has really changed its moral values. I have two examples. Slavery. Okay, we haven't gotten rid of it, and I'm not saying we've gotten rid of racism, but if 200 years ago there were human beings that were just not regarded as full people, it would be very hard to find people today in our country who espouse that with any conviction. That's been an enormous sea change. So this is exactly what you're talking about how we have close by comrades and our feelings become more diffuse. I would say that as time goes on, recently, we are getting better and better at bringing new creatures, new people, new entities into our tent and thinking about them as we think about themselves. This is really remarkable. So slavery is one example. I would say rights of women are another. I would say endangered species. is another example. And this is a trend that's happening. Do we need to take advantage of this, understand it, and use that momentum to bring the future generations into the tent?
Right.
So I like the concept of the expanding tent, and how do we manipulate that?
Mm-hmm.
I don't know. I think this is actually a research question.
Yeah, so it seems to me some of the positive expansion could even be considered self-interest, like say the European Union. You know, the idea that it's still self-interest, but they decided that thinking more broadly would have positive impact both personally and generally.
Yeah, sure. Mm-hmm. But I'm, as you can tell, I'm doing a little bit of reading about the origin of moral codes. And there are people who say, looking at this in a very cold-blooded way, that you do not have a moral relationship with another being, let's say between two people, without having a transaction, either immediately between the two of you or foreseeable between that person and somebody you care about. So there's a theory of morality and value generation that is based on a transactional model. A challenge is, how do we get a transaction going between our generation and a future generation? The transaction in question is two-sided. Things flow in both directions. How do we get something to flow from a future generation to us?
Well, we have to save their environment first.
And you did say we were going to accelerate beyond the speed of light, which could bring in more.
This is a little bit off topic, but how are you, in terms of being able to do research? Right now, there is so much satellites up in the atmosphere, and I'm a photographer and I like to take pictures of space. And now there are so many satellites and there are more being launched. How does that interfere with the telescopes and the radio telescopes' ability to see up there? I would imagine the optical ones that would, especially if they're Earth-based. Is there any kind of transaction or any kind of talking back and forth to see if we can't limit our space junk isn't the right word, but that's what I feel like when it goes past.
Yeah, right. Well, I suspect that you're taking much wider angle pictures than big telescopes take. So in fact, the probability that a satellite goes through one of our fields of view, it would go through extremely quickly. Our exposures are kind of long, so we might not even see that happening. Sometimes astronomers like to share these rare, weird pictures in which, aha, a satellite went through my observation. But it's rare. It's not really a problem, at least not yet.
Airplanes are a much bigger problem around here.
Right, that's for sure true.
Are your slides going to be available? Someone asks.
Sure, I'm happy to make them available. Maybe I should talk with David about how to do that. Yeah, share them. Share the ideas, get conversations going, and if something interesting comes back, especially on these bigger questions, you can see I'm looking for new thoughts, new directions. Get back to me on that. I'd really appreciate it.
Hey, Sandra, do you think becoming a multiplanetary society changes sort of our perspective on this? I mean, is that going to, give us a longer runway, or are we just effectively doing, replicating the same thing somewhere else?
Yeah, that's a really good question. So I think we're going to be saved from that fate by the fact that the available planets are not interesting. So Venus is out of the question. People talk about terraforming Mars. Those people really ought to be challenged, first of all, to grow corn in Antarctica because it's a much harder job to terraform Mars. Furthermore, we shouldn't look at Mars as an escape valve. It's a small place. I don't know what the surface area is compared to Earth, but maybe a quarter or something like that. So wouldn't it be easier to restructure ourselves at the 25% level than to terraform an entire new planet?
Yes.
Okay, so I think for that reason, we are going to have to come to grips with our local problem first. Mars is not going to solve it for us. We're going to have to do that here on Earth. Am I in favor of planetary exploration for other reasons, just for the exploratory value, the experience, the gained understanding, intuitive understanding of the cosmos and what it can do? Of course, I'm in favor of that. But that's a whole different set of reasons. That's not the reason I usually hear. So I tend to be anti these days, but it's not fundamental. It's because how people are justifying it.
So you raised a couple of moral questions. So the question is, my question is, who gets to decide? Who gets to decide who is, if the Earth can only support so many people, who gets to decide who makes the cut?
Well, if we look at other species, it's not going to happen in any pretty way. So as some people say, it has to get worse before it gets better. I just don't think people see the urgency right now. I look out my window. I wish you could look out my window. I see blooming plants. I see trees that seem fine. It's a blue sky, especially here in Northern California. What's the problem? No. And we just don't see the problem until it's a daily burden. And I don't know how long that will take. I think it is possible, though, that we can respond as a species when it's apparent to everybody that we've got a problem. But I think deep down in our hearts, we don't believe it yet.
It does seem like the younger generation is really facing or understanding the climate change threat, at least. Do you agree with that?
I think yes, to some extent, but I think people have really no idea of what they're asking for. Mm-hmm. So I think our immediate problem is the economic system, mm-hmm. which has to grow. And this is why conversion to sustainable fuels is just not getting any momentum, because that machine needs profits. It needs to expand on an annual basis. And it's true we're getting somewhat more efficient in producing GNP per barrel of oil. Unknown caller. But excuse me for just a moment. Hi, I'm going to have to call you back. I know it's Danielle, but I'm on the phone, okay? Yeah. But the gains that we're making there are just not nearly fast enough with a problem that is extremely fundamental. So yes, you can demonstrate, but I don't see the program, really, the realistic program. Actually, the near-term Band-Aid is nuclear power.
Can I get back to astronomy for a minute? This is Andy, AE6Y. First, two things. One is I'm always astonished when I listen to you or your colleagues that you claim to know all this stuff. And you pointed out yourself, it's ridiculous to talk about 10 to the minus 35 seconds and the laws of physics jumping into effect, or at least we understand them at that point. Mm-hmm. And you do all this without doing experiments, and you just observe. It's incredible.
Oh,
in the sense that you don't touch
say that the universe is a giant experiment.
Right, but it's unlike chemistry. You don't cut something open and burn it and then look at the element. Everything you do is by looking at electromagnetic radiation of one form or another. Mm-hmm. And I think that's kind of mind-boggling. But getting back to some of the things you were talking about, dark energy is the most amazing sort of concept, and it's relatively new in terms of our understanding, I gather. So when are we going to figure out what it is and what are likely candidates?
I'm not optimistic for my lifetime. The problem is that there's a characteristic temperature for these energies. So the first energy, which was the scalar field of grand unification, has a characteristic temperature of 10 to the 27th degrees. And we already knew that that was a characteristic temperature before people began thinking about inflation in cosmic terms. We knew it was a characteristic temperature because we had a theory of electromagnetism, we had a theory of the weak force, we had a theory of the strong force. We could see that each one of those was energy dependent. The coupling constants evolve as a function of energy, and people would draw these diagrams showing that, oh wow, all those coupling constants are going to intersect, 3 of them, in a single point, which corresponds to a temperature of 10 to the 27 degrees. So there was already a predilection that there was going to be, maybe in the history of the universe, there would be something special there. That was a great breakthrough of the early 1980s. The problem is that the characteristic temperature of dark energy, as we know it, is like 6 degrees Kelvin. Go back in time a little bit when it began to set in. And we don't have any physics that produces anything at that low energy. So people are writing down equations, making up entities that behave differently as a function of time, et cetera. At the moment, I don't think it's being very productive. For me, much more interesting and likely at the moment is that it is a true cosmological constant, but then we have the problem of where it came from. It's like big G, it's like the electron charge and so on. We could only describe it anthropically to say that, yes, it's another number in the ensemble of universes, and ours is the way it is because if it were any bigger, then we would have inflated a long time ago as a second inflation, and that would have impeded the formation of galaxies. So there's sort of an upper limit on this lambda, and this lambda is right where it needs to be at that upper limit. It could be its value or smaller without impairing galaxy formation as we know it. But that's not a theory for where it comes from. I feel very pessimistic.
So is strength, how can I ask this? Are there alternatives to string theory that are also being proposed? I was under the impression that string theory was somehow falling out of favor a little bit.
Yes, and now I'm embarrassed because I can't answer these questions very sensibly in this area. Sure, there have been changes to the mathematics, and now people talk about membrane theory or M theory. Instead of strings, we have higher dimensional entities here. I'm not following that, to be totally honest. I think the basic implications, though, are still the same. That is to say that there's this 11-dimensional thing which can do lots of different things. It's a very potentially creative thing that can make all different kinds of universes. You should get somebody to talk about that. Would you like some? I could probably find somebody who give you a talk on it.
Maybe.
Yeah.
We have experts on this at Santa Cruz in the physics department.
Well, it's 3 o'clock, so that's the supposed to be the official end time. But people are welcome to hang out. And Sandra, thank you so much. That was great. And
great. Yeah. Well, I enjoyed it. It's the best question session I've had for this talk. So it's nice that you were willing to sit through it and give me a little extra time.
Here, here. Wonderful. Wonderful.
Thank you. I learned a lot. Woo. Thank you so much. Very good. Thank you.
Very okay, good. Thanks all. Thanks. Bye.
Bye. Thank you very much.
Thank you.
Thank you very much.
Thanks a lot. I hope this has
Don't
been
turn me off because I was going to look at the chat, which would be interesting.
I think we'll all be here for a little while. I think we have a post